Okay, so we know that the null space of, so if we have this homogeneous system, for example, AX equals 0, where A is some m by n matrix, and this is just the matrix form of the normal linear system that you're used to, in this case a homogeneous system, because everything on the right hand side is 0. And x is, as again, it's a vector, so it is a m by n by 1 vector that is a solution to this particular equation. Now we know that given this, we know that the null space, or the space of all solutions to this equation, in other words, all the vectors that satisfy, all the vectors x that satisfy this equation, is a subspace of Rn. Well, very important question, a very important problem is finding a basis for this subspace. And if you recall what a basis is a set of vectors that actually spans the entire space that we're dealing with and is also linearly independent. So you remember, you might have a series of vectors that span a space, but they might not be linearly independent. Or you might have some vectors that are linearly independent, but they might not span the space. A basis is something that satisfies both of those properties. Again, it spans the space that we're talking about, and the vectors are linearly independent. In this case, the space that we're talking about is the null space, the space of solutions to the homogeneous system AX equals 0. Okay, so the procedure for finding a basis for the null space of AX equals 0, where A is m by n. Of course, I won't go ahead and mention that. The first thing we do, well, we solve. AX equals 0 by Gauss-Jordan elimination to reduced row echelon form, as always. Now, if there are no arbitrary constants, in other words, if there are no columns that have no leading entries, then the null space equals the set, the 0 vector. What that means is that there is no basis for the null space. There is no null space, essentially. Well, there is. It's the 0 vector, but there is no basis for it. In other words, there is no collection of vectors. Okay, and the dimension of the null space, which we called the nullity, if you remember, equals 0. Okay. Our second possibility is if arbitrary constants do exist after we reduce it to reduced row echelon form. And what that means is if there are columns that don't have leading entries, those are the values corresponding to those columns. Let's say it's the third and fifth column, so x3 and x5. I can give them any value I want. That's what the arbitrary constant means. So if arbitrary constants exist, then write the solution x equals c1x1 plus c2x2 plus dot dot ck, xk, however many of these vectors and constants there are. Well, once you do that, the set S, which consists of this x1, this x2, all the way up to xk, x1, x2, xk, is a basis for the null space. Let me write space over here. So again, what we do when we want to find the basis of the null space of a homogeneous system, we solve the homogeneous system with reduced row echelon form. We check to see if there are no columns that don't have a leading entry, meaning if all the columns have a leading entry, there are no arbitrary constants. Our null space is the zero vector. It has no basis, and the dimension of the null space, the nullity, in other words, equals 0. Let me go ahead and put nullity here. Nullity is the dimension of the null space. In other words, it's the number of vectors that span that space. It is 0. If arbitrary constants do exist, meaning if there are columns that don't have a leading entry, then we can read off the solution for that homogeneous system. We can write it this way, and the vectors that we get end up being our basis. Let's do an example, and as always, it'll make sense, hopefully.